So what I'll have a quick chat about is what happens if you've got thermal motion in our chain of atoms. Hopefully it'll be acts as revision as well, because it will separate out a little bit of the maths we did with the quantum mechanics, with the 1D type binding model. Hopefully it will separate out the bit where we're looking at a periodic chain, so effectively a Fourier transform that we did to get our solutions. Separate that from the fact that we were doing quantum mechanics. So maybe it'll make it a bit clearer which bit's the quantum mechanics and which bit was the fact that it's periodic and we solved it in a particular way. So let's go back to our model. I've got 1D chain of n identical atoms. So literally we've got atom, we go along a distance a in the x-axis, and we've got another atom. We go along a distance a in the x-axis, we've got another atom. Go along distance a, yeah, there's a, and it's going to be crystalline in the end. What we're going to do is going to set up the same model as we had before. We're going to have n atoms in our chain. Yep, Chris. I am recording, but I'm doing it locally. Blackboard's got a resolution of I don't know, a myopic drunken fly or something. But do remind me to actually upload the. I suppose. Yeah, I don't know. It gets very fiddly. I shall check I am recording here. Yeah. So we've got this chain of n atoms, and we're going to find the equilibrium position of each atom to be the number of the atom times A, as in they're on these grid points. First atom at 0, A, 2A, 3A. We're only going to do a 1D model so they can oscillate along the direction of the chain. That's the only direction of movement. What I was expecting. So what we're going to do is have a harmonic spring between each of the different atoms. So we know sort of quantum mechanically that there's going to be some more complicated interaction potential between the atoms. But if they're very near their preferred location, then any type of well, as long as you're close enough to the bottom, we can approximate it as a harmonic potential. So we can fit a parabola around the bottom of the potential well. So what we're going to do is, no matter what the interaction potential really is, what real type of quantum mechanical interaction, if we're at some sort of low enough temperature so that the atoms are only moving near the bottom of the well, we can approximate the interaction potential with a harmonic interaction. That means that the energy changes quadratically as we move the atoms away from their equilibrium position, and it means it's equivalent to a force that's linear on the displacement. So there's some spring constant, effective spring constant, which we'll call kappa as we move the atoms. So what we are going to write our total potential energy of our system as the sum of the interactions between neighbouring atoms. So what we're doing is, for each pair of atoms we check whether they're next to each other in the chain, and then if they're in the chain, effectively we're going to put in a spring between them, or this quadratic interaction. So we work out the distance between the two atoms, and if it is different from this A, our preferred equilibrium distance for the atoms, then we add on a quadratic term which is proportional to the difference. So if I look at this expression here, I've got the position of the I plus 1 atom minus the position of the ith atom. And if they're happy little atoms, that will be A, that will be the distance I want to be at. And then I'm subtracting the preferred distance, our x0. So displacement minus the sort of preferred distance. So the distance between two neighbouring atoms minus A, our equilibrium distance, and we're squaring it. So that's our potential energy. And we add it on to each. And what we're summing over all the atoms. And we've got a half, because this way of doing it, we would count we would count each interaction twice, because no, we wouldn't. You can ignore that comment. The half is just the way we've defined it, that the potential energy is half kx squared. And we can rewrite this, if we like, in terms of not this positions of them, but in terms of displacements. So the potential energy is this exactly the same thing. So the how far the first atom is from its preferred position, what's the displacement of the second one from its preferred position, and square that. So both of them are at their preferred positions at 0, and if they move, then get that. It's exactly cool. Then we can get the force by taking the partial derivative of our potential energy function with respect to the individual coordinates. So the energy expression is quadratic. When we take the derivative, effectively we've got a chain rule expression. This is a squared thing, so we'll get a 2, and inside the bracket we've just got something that's proportional to the coordinate we're talking about. What we will get, but each coordinate's going to appear twice, once when it's the atom on the left and once when it's the atom on the right. We will get 2 terms. But essentially this is 2 springs, one either side. So the force on an atom, as we've taken the derivative with respect to the nth coordinate, will be our spring constant. We've got the same spring constant for all the atoms. So it's how far apart this atom and its neighbour to the right are, how far they're away from where they should be. That will pull it one way. And then there's another term, that the atom with the one to its left. Then we write out Newton's equations. Where did I jump to this from? I'm just being daft. Yeah, they're just Newton's equations. So I've got my equation here. So this is my force in terms of the springs, and that is just going to be equal to the acceleration of that So for each atom, I've got an equation, one of Newton's equations for its motion. So I've got n equations, and I've got n unknowns in the displacements of the n atoms. So I've got a set of simultaneous equations, so we should be able to solve it for these displacements of the atoms. I think I've, as normal, got something very simple and I've managed to make it look a little bit complicated. But essentially we've got Newton's equations for each of the atoms. Each atom's got two springs attached to it, one for the atom on the right, one for the atom on the left. And the displacements, the force backwards depends on the distance between this atom and its one to the right, and then this atom and the one on the left. So once I set this up, I get n equations. So ma equals this force on the atom, which is dependent on the position of the atom itself and its two neighbours either side. That defines these extensions of the springs. And then we're going to do exactly the same trick that we did for the quantum mechanical system. We're going to say, well, we know that our system is repeating periodically, so we must have some sort of periodic solution. There must be a Fourier type of solution, a periodic system, a periodic solution to our displacements. So we're going to say that the displacement of the nth atom is going to be written in this form, a, and then a complex exponential I omega t minus I k, which is some wave vector. Na is the position of the undisplaced atom. So that's going to make it periodic, it's Na. If I move further along, then every time I go along this complex exponential is going to repeat itself. So A, omega and K are the amplitude, frequency and wave vector of the proposed wave. Then we plug, so if you look, I've got this dxn, second derivative with respect to time on the left, and just the different the dx's for three different atoms on the right. So we plug in our proposed solutions into those equations. The second derivative with respect to time on the left-hand side is easy. That's kind of why this method works. We'll do solution of differential equations using Fourier transforms with Martin next year if you're doing methods of mathematical physics. With some more detail. But we get this minus omega squared appearing on the left, and on the right we get these expressions here. So there's this n plus 1 and n minus 1 because they're a further or less further along the chain for the different coordinates. So we're plugging in the delta xn for the different ones, and this Na is the x position of the nth atom. So the n minus 1th atom, this should be an n minus 1. So once I plug it in, I get this original solution plus this stuff here. Then I can cancel out the time dependence because I've just got this ei omega t on both sides, and I can divide through this by this e to the I k n a through there, and what I get is in this bit here, this ikna bit cancels out, but I get left with plus and minus ka e to the I ka, which is another way of saying a cosine ka. And then you can use this double angle formula to rewrite that in terms of a sine squared if you prefer. The setting up Newton's equations, the quantum equivalent of that was setting up these matrix equations for the Schrödinger equation. But then for the quantum thing, we had the coefficients of the wave vector, and we said that they should change periodically along the system, so that we could write them in terms of e to the I kx. In this case, we're saying that the displacements of the atoms should be periodic for any thing. We have some sort of resonance where they're all moving in or out of phase with each other. So again, we put a trial solution that's periodic in the displacements. And so what we get in the end, so I've got an omega square here, which came from the second derivative with respect to time of our trial solution. And we've got this sine squared here, so if you take square root, we get that the frequency is equal to 2 square root of the spring constant divided by the mass, and then this sine Ka upon 2. This is called a dispersion relationship. It connects the frequency and the wave vector of a mode of oscillation of the system. So this K that you see in the quantum case is not particularly quantum, it's just something that comes from having a periodic system. If we've got a set of springs along a chain, or a set of atomic wave functions that are connected by a hopping integral that go from nearest neighbours, or springs go to nearest neighbours, the mathematics is very similar, but the sort of physical meaning of solutions is a bit different. And I think the last bit to say is sound waves. So sound waves are very long wavelength oscillations. So if we take this solution that we got for the dispersion relationship and say, okay, very long wavelength, and a very long wavelength means a very small wave vector. So the wave vector is essentially 1 over the wavelength. So in this case, so for very small wave vectors, we can make a small angle approximation. So we say sine of Ka upon 2 is approximately equal to Ka upon 2. And so then we get that the frequency is proportional to the wave vector. And the proportionality constant is this square root of the spring constant over the mass times the displacement. The lattice constant, the separation of the atoms. And so the phase velocity, or the speed of the motion of the wave along the chain is given by either the frequency divided by the wave vector, or the derivative with respect to the wave vector. So that's either whether it's the group velocity or the phase velocity. But in this case, they should both coincide and give you this expression. And so a sound wave is this small wave vector solution, and indeed the phase and group velocity should be the same, so with the derivative, whatever. So it basically means that the frequency and the wave vector are proportional to each other. So in this case, we've got it. So in general, there is a sound wave if you have a solution that has this form. So for small wave vectors, there is a solution there that is proportional. We've got frequency proportional to the wave vector. So this is the speed of sound in our 1D crystal. So the speed of sound will increase if there's a bigger spring between the atoms. So if you tighten the spring and sort of flick them, you get a faster response. If the lattice spacing is bigger, everything else being equal, you get a faster sound wave. So as the wave travels, the atoms are further apart. But this is quite similar to the tight binding model again for this sort of effective mass, same thing. Further apart the atoms are when they hop, the quicker they or the farther they move for each hop. So anyway, it makes sense. Stronger spring, lighter atoms, and bigger crystal. All of those give you a faster speed of sound. And as a last thing I want to mention, the thermal expansion. So this model, we've got this harmonic quadratic thing. So as you heat it up, the atoms will explore more and more of the potential energy surface. They can roll further up the hill either side. Then the quadratic potential, the two sides of the hill are equally steep, and the average distance that a particle rolling around in that well will still stay at the equilibrium distance. It won't change. So it will, at zero temperature, it likes to be at the bottom. And for a quadratic thing, even though it's rolling up and down, on average, both sides are the same. It will keep exactly the same distance. But in a real potential, like something that's a bit like this Leonard-Jones, or what you would get from the quantum mechanical model, sort of fully including the repulsion as the atoms get close together, or as they get further away, relaxing. It's anharmonic, and it's steeper on the left as they get close together than it is on the right as they get further away. And this means at a temperature, as you let the atom roll around sort of higher up the curve, if you take the average displacement, as the temperature increases, it moves to the right because the potential is softer on this side. There's a classical mechanical result. If you've got a potential that's anharmonic, as you increase the temperature, the average displacement will shift towards the softer side in the anharmonic potential. So this is a model for what would happen as you increase the temperature. The anharmonic potential will cause the average distance between the atoms to increase. And then I'm going to stop here, but there's a bit, this analogy of this wave vector with this reciprocal lattice and the type of solutions we got with the quantum system at the same. One last thing to mention is so-called quantum correspondence principle, which is every time you have a classical harmonic potential or a classical mode of oscillation, there's a quantum equivalent. So each of these harmonic oscillators that we had in this model that we just solved, each of those, we had n springs in harmonic oscillators, we coupled them, whatever, got these solutions out. So-called normal modes are these different solutions characterized by this dispersion relation. So each of them will give rise to an equivalent quantum mechanical state. And for vibrations, we call the quantum version of the vibration, we call it a phonon. That eventually answers that question. There's other types of vibration, but actually photons kind of come from vibrations of the vacuum. Discuss that with Fabienne if you want a good line. This stuff is. I won't go into it, but that was all atom, 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 each atom the same, each string constant the same. If you make it more complicated crystal, for instance, one you could go to 3 dimensions, or the other way, if the atoms were sort of A, B, different atoms with different lengths, masses, or spring constants, basically everything becomes the same, but your unit cell is a bit bigger, and you have different types of interactions. And you can write, but you'll still get n simultaneous equations, but you can link them there. And what you would end up with is different simultaneous equations for the different types of atoms. Again, you could write them in a matrix, and you could follow through with more or less the same type of solution we had before, but you'll get a matrix that comes out, and you can solve. So for 2 types of atoms with different springs between them, you get this type of matrix solution that comes out, and then you can solve that to get the frequencies of oscillation. So don't worry about that last bit, but just to be aware that the 1D model becomes more complicated. You get multiple solutions, but you should still find this one acoustic mode that looks just like the simplest model we had, but then you'll get more complicated modes sort of up above it, do slightly different. There are sort of another sort of more in-depth version of this lecture that you can see online there, and some things where you can get some animations and stuff to look at. Right.